Load balancing. In section 13.1, we consider a distributed system in which communication among processes was difficult and randomization to some extent replaced explicit coordination and synchronization. We now revisit this theme through another stylized example of randomization in distributed setting. The problem. Suppose we have a system in which m jobs arrive in a stream and need to be processed immediately. We have a collection of n identical processors that are capable of performing the jobs. So the goal is to assign each job to a processor in a way that balances the workload evenly across the processors. If we had a central controller for the system that could receive each job and hand it off to the processors in a round-robin fashion, it would be trivial to make sure that each processor received at most the ceiling functions of m divided by n rounding up jobs, the most even balancing possible. But suppose the system lacks the coordination or centralization to implement this. A much more lightweight approach would be to simply assign each job to one of the processors uniformly at random. Intuitively, this should also balance the jobs evenly, since each processor is equally likely to get each job. At the same time, since the assignment is completely random, one doesn't expect everything to end up perfectly balanced. So we ask, how well does this simple randomized approach work? Although we will stick to the motivation in terms of jobs and processors here, it is worth noting that comparable issues come up in the analysis of hash functions, as we saw in section 13.6. There, instead of assigning jobs to processors, we are assigning elements to entries in a hash table. The concern about producing an even balancing in the case of hash tables is based on wanting to keep the number of collisions at any particular entry relatively small. As a result, the analysis in this section is also relevant to the study of hashing schemes. Analyzing a random allocation, we will see that the analysis of our random load balancing load random balancing processes depends on the relative sizes of m, the numbers of jobs, and n, the number of processors. We start with a particularly clean case when m is equals to n. Here it is possible for each processor to end up with exactly one job, though this is not very likely. Rather, we expect that some processors will receive no jobs and others will receive more than one. As a way of assessing the quality of this randomized load balancing heuristic, we study how heavily loaded with jobs a processor can become. Let xi be the random variable equal to the number of jobs assigned to processor I for I equals to 1 to 3 until n. It is easy to determine the expected value of xi. We let yij be the random variable equal to 1 if a job j is assigned to processor I and 0 otherwise. Then xi is equals to the summations of yij, summing with index I starting from 1 to n, and the expectations of yij is equals to 1 over n. So the expectations of xi is equals to the summations of the expectations of yij, summing with index j starting from 1 to n, which is equals to 1. But our concern is with how far xi can deviate above its expectation. What is the probability that xi is greater than c? To give an upper bound on this, we can directly apply 13.42, the Chernoff bounds. Xi is a sum of independent 0, 1 valued random variables, yij. The set of yij, we have mu equals to 1, because we just derive it, and 1 plus delta, we set it as c. Thus, the following statement holds. 13.44. The probability of xi greater than c is less than e to the c minus 1 divided by c to the c. In order for there to be a small probability of any xi exceeding c, we will take the union bound over I equals to 1 to 3 until n, and so we need to choose c large enough to drive the probability of xi greater than c down well below 1 over n for each I. This requires looking at the denominator c to the c in 13.44. To make this denominator large enough, we need to understand how this quantity grows with c, and we explore this by first asking the question, what is the x such that x to the x is equals to n? Suppose we write gamma of n to denote this number x. There is no closed form expression for gamma of n, but we can determine its asymptotic value as follows. If x to the x is equals to n, then taking logarithms gives x log x is equals to log n, and take logarithms again gives log x plus log x is equals to log n. Thus we have 2 times log x is greater than log x plus log x, which is equals to log n, which is greater than 766 log x. And using this to divide through the equation x log x is equals to log n, we get 1/2 times x, which is less than equals to log n divided by log n, which is less than equals to x, which is equals to gamma of n. Thus, gamma of n is equals to the theta of log n divided by log n. Now, if we set c equals to e times gamma of n, then by 13.44 we have the probability of xi greater than c is less than e to the c minus 1 divided by c to the c, which is less than e divided by c, then to the c, which is equals to 1 divided by gamma of n to the e times gamma of n, which is less than 1 divided by gamma of n to the 2 times gamma of n, which is equals to 1 over n squared. Thus, applying the union bound over this upper bound for x1, x2, x3, and so on to xn, we have the following. 13.45. With a probability at least 1 minus n to the minus 1, no processor receives more than e times gamma of n, which is equals to theta of log n divided by log n drops. With a more involved analysis, one can also show that this bound is asymptotically tight. With high probability, some processor actually receives omega of log n over log n drops. So although the load on some processors will likely exceed the expectation, this deviation is only logarithmic in the number of processors, increasing the number of drops. We now use Chernoff bounds to argue that as more drops are introduced into the system, the loads smooth out rapidly so that the number of drops on each processor quickly become the same to within constant factors. Specifically, if we have m equals to 16 times n log n drops, then the expected load per processor is mu equals to 16 times log n. Using 13.42, we see that the probability of any processor's load exceeding 32 times log n is at most the probability of xi, which is greater than 2 mu, which is less than e divided by 4, then to the exponent of 16 times log n, which is less than 1 divided by e squared to the log n. If we cancel out the terms 4 with 16, then we take the exponent of log n, e to the exponent of log n down to the 1 over e squared, which is equals to 1 over n squared. Also, the probability that any processor's load is below 8 log n is at most probability of xi less than 1/2 times mu, which is less than e to the minus 1/2 times 1/2 to the square times 16 times log n, which is equals to e to the minus 2 times log n, which is equals to 1 over n squared. Thus, applying the union bound, we have the following. (13.46) When there are n processors and omega of n log n jobs, then with high probability, every processor will have a load between half and twice the average.